Good morning, everyone, and welcome at this second session of the webinar event. So yesterday we had a nice session of webinars focusing on EV charging, best practices in general, and today the focus will be more on power quality. So we would like to mention that it's still possible to register for the other events we have later this afternoon. You can do this via the ElaadNL website, and also afterwards all sessions will be visible on the YouTube channel. So please keep an eye on this as well, and subscribe for the YouTube channel to keep receiving the updates. So Thijs and I will be hosting this series of webinars. This session I will be hosting, and Thijs will be collecting the questions. So you can use the question box of the GoToWebinar menu to ask all your questions to Helko, and then I will ask them afterwards to him. Also, this event has been made possible by the Horizon 2030 project Progresses, which is focusing on improving the efficiency and grid integration of the next generation energy supply infrastructure. So this presentation is from Helko van der Brom. He is a principal scientist at VSL, that's the Dutch National Metrology Institute, where he's involved in the electrical measurements, mainly researching power quality, electricity meters, current and voltage transducers, and the sampling systems. And he will be presenting about electromagnetic interferences between DC and 150 kHz, something about beyond current standardization. So really looking forward to the presentation. I would say, Helko, the floor is yours.
Thank you very much, Tim. Thank you for the invitation and for the introduction as well. And all of you also hello and welcome to the presentation. This is on lacking standardization of electromagnetic disturbances between DC and 150 kHz. As Tim said, my name is Helko van der Brom and I work at VSL in Delft. For those of you who do not know us, VSL is the National Metrology Institute. That's a difficult word. It's something different from meteorology, which is also a difficult word. So what I'd like to say, most of the metrology institutes are governmental organizations. And VSL is an exception in that it's a private company, and typically about 110 people work at VSL, and say half of them, or 40%, has an academic background. The core business is calibrations and reference materials, research and development, and consultancy and training in the field of metrology, with a focus on energy-related issues and also industrial topics. We are located here in Delft, in the Netherlands. Okay, so the main topic of today's web event is power quality. And as you know, power electronics and converters in EVs and EV charging stations are causing disturbances that are not yet all covered in present standardization. So today I want to show you 3 European metrology projects on power quality that are in support of improved standardization. The first of them is the influence of conducted EMI or power quality on electricity meters, such as installed in residential meter cabinets or EV charging stations. This project is just finished, and I'd like to show you the highlights. The second topic is how to reliably measure 2 to 150 kHz disturbances. This is a running project. And the third topic is power quality and disturbances in DC microgrids that could also potentially facilitate EV charging. This project just started, so I can only tell you what we are about to do and not what we have done. Okay, so the first topic is on the effect of disturbances on energy registration of electricity meters. And that started with the work of University Twente, shown here in the Netherlands in 2015. That has led to this paper. And the study was triggered by really substantial doubt on increased energy bills after the replacement of the old-fashioned Ferraris meters by the new static electricity meters. And in Twente, they supposed that EMI could cause these problems. And in their laboratory, they performed some tests. These tests aimed to upset the meters by disturbing electrical loads. And they showed indeed that static electricity meters showed enormous reading errors when exposed to specific conducted EMI. This was then picked up by the media in more than 20 countries, which led to alarming headlines like these. And of course, customers and network operators and governments were shocked, which led to an urgent need for independent confirmation and further investigation. That is why Netbeheer Nederland, the Dutch Sector Association of Network Operators, asked VSL to verify these Twente studies with independent and traceable measurements. And to do so, we took the same 4 meters as used in Twente, shown here, and the electromechanical meter that they used as a reference, which is shown here, and a similar phase firing dimmer, resistive heater, and series of CFL and LED lamps, shown here. And furthermore, we added 5 other meters, shown here. But instead of using an electromechanical meter as a reference, we used our own reference system with calibrated broadband voltage divider, current shunt, and high precision digitizers. And a computer was used to read out the digitizers and optical pulse signals from the meters under test. And in summary, we confirmed the findings of the University of Twente. First of all, the observations of Twente and VSL showed that distorted current causes, in fact, the error reading, so not voltage but current. And the recorded waveforms were very broadband, as you can see here in the figure on the right, which means that this is not a pure conventional, so to say, 2 to 150 kilohertz problem. The difference is that we see many components at the same time versus a single tone in the conventional measurements. So the real cause seemed to be high and fast current peaks, which means large current and large slope, the IDT. And we also found that clearly the type of current sensor is relevant, but that there are other issues too, with for instance, software or hardware related. The conclusion was that a combination of specific signals with specific static meters showed enormous errors, and that details on the influence and details influence actually the size, but also the sign of the meter error. So it could also be very strength to low energy. We extended this work by measuring a wide range of electronic appliances. And as mentioned earlier, the peak current and the IDT were the most important parameters. So what we did is we categorized the measured waveforms in terms of these 2 parameters and plotted them in the graph that you see here on the right. And as you can see, most signals are found in the lower left corner, which means low the IDT and low maximum current. And the circled points are the ones causing the largest reading errors, as we have seen. These include the original Twente signals, but also a specific water pump with an internal dimmer. And it seems actually that dimming is involved in all of the most disturbing signals. So this raises the question, what interference waveforms do occur at real meter supply points, such for instance in our homes or in EV charging stations. Also, is there a benchmark meter that is immune to these waveforms to settle billing disputes between customers and utilities, for instance? And do these waveforms also cause errors in MID approved meters? And what new test beds might be needed to approve meters with these new real-world waveforms? And what new test waveforms might be needed to test meter performance? So these were the key questions addressed and answered in the Meter EMI project, which I will show now. First of all, in addition to the signals from specific electronic appliances, we also wanted to know what happens at connection points with static electricity meters in the field. And that is why several of the project partners set out to different places. Here you can see that the University of Catalonia in Barcelona, together with the University of Twente, measured an EV charging station. At the top right, you can see a picture, a photo of where the measurements were taken. And at the bottom left, you can see the method of connection. And at the bottom right, the measured current signals are shown. And you can see that they contain quite sharp peaks indeed. I will show the effect of such on-site signals on electricity meters later. At VSL, we've developed an on-site waveform recorder that goes one step further, actually, by also registering the energy consumption. This meter was shown to be more or less insensitive to interference signals and can be connected in parallel to already installed energy meters for a week or so in order to see if there's any difference in energy reading. It is a three-phase waveform recorder with broadband components and special matched input filters between voltage and current signals, such that they are properly multiplied in the equation, the integral equation. It also measures the energy continuously, but it can be used to record voltage and current waveforms at specific time intervals or when triggered by specific threshold values of the IDT or the crest factor or other parameters. The uncertainty is proven to be better than 2%, even for the most extreme waveforms. I will show you later how we do that. Now we want to test the immunity of electricity meters for the highly peaked and broadband waveforms that we have measured before. In a conventional split signal testbed, as presented in the 61000-4-19 standard, the disturbance signal is injected using a separate injection circuit. This works fine for single tone signals and small disturbances, but not if they are as broadband and severe as we've seen here. So therefore, we developed an arbitrary waveform testbed, as shown here on the right. The test signals are applied through an arbitrary waveform generator with a voltage amplifier and a transconductance amplifier. The current is then measured through a broadband precision shunt, and the voltage is measured through a broadband resistive divider. The data are sampled with 1 megasample per second, such that we at least capture frequencies sufficiently high. Then an optical sensor is used to register the energy reading of the meter under test. And the meter error is then determined as the relative difference between the meter reading and the reference setup. So apart from calibrating the individual components, the setup has been independently validated by comparing the waveforms recorded to the waveforms sent to the generator memory, and by comparing the results of the test bed to those obtained using the original setup with real loads, as presented a few slides before. Okay, and in the meantime, we have tested a lot of meters with this test bed and also the benchmark meter that I presented in the previous slide. So that's why I know that this benchmark meter is also good. Okay, Then here we see some results when we use the testbed to test a set of, in this case, 16 electricity meters, which were from 10 different manufacturers that have been rolled out between 2008 and 2019 in 6 different European countries. And they have different types of current sensors. That is shunt, Rogowski coil, current transformer, a Hall sensor, and in some cases we don't know what it is. The test waveforms in this table are from several appliances with dimmers, such as a resistive heater, a combination of CFL and LED lamps, and a specific water pump that I mentioned before. And the waveforms are applied without further loading, so only those waveforms. The 16 meters themselves are indicated in the column headings here with the corresponding sensor type and year of manufacturing. And the waveforms are indicated in the rows on the left with their corresponding power content if they are combined with a 230 volt sinusoidal voltage signal. Now I don't expect you to read all the numbers, but the colors speak for themselves. Green here means okay within 2%. Blue means that it's more than 10% less energy recorded, which is good for you. And red means more than 10% too much, which is bad for you. You can read, you can actually see that several meters show enormous errors, either with energy readings too high or too low. And roughly speaking, we can see that the relative errors are largest for low power signals, where the power is concentrated in a very sharp peak. And in the most extreme cases, you can see that this leads to errors of up to several thousands of percent. So this is only for household appliances. And earlier I mentioned that on-site measurements were carried out at metered supply points by project partners UPC and Twente, among which like EV charging stations. And in addition, at VSL, we received some waveforms from various network operators that were recorded with the waveform recorder that I presented a few sheets before. And several of these waveforms were used to test the same 16 meters, and results are presented in this table. So here we found several meters with meter errors as well. I won't go through the details of the table again, but the colors speak for themselves. So for us, this was actually quite an important result, because in the early days, the objection was always like, yeah, but those earlier signals were measured in the laboratory, and that is very artificial. That doesn't present real life. So these signals are not, they are really recorded at metered supply points right in front of the meter. So they really come from meter cabinets like yours or mine at home. So roughly speaking, we see in the table that the older meters are the most prone to errors, but a sample of meter A14 on the right from 2019. This one is at 2013, but we also had one from 2019, and it showed the same behavior. And that meter was actually tested also against the IEC 61000-4-19 for signals between 2 and 150 kilohertz. And obviously, the current standards are not sufficient to cover these real-world distortions. Okay. So what we also did is, for future uptake of the relevant test waveforms in potential updated standards, project partners NPL and UPC have developed methods to simplify the description of the recorded signal, such that only a few parameters are needed to construct the waveforms. And such simplifications are illustrated here for the water pump signal mentioned before. Note the time scale, actually, it's in milliseconds, so it's a very sharp and narrow peak. The left figure shows a wavelet decomposition, which is more precise, but still quite complex. And the right figure shows a linear approximation of the same waveform based on only a few fixed points, keeping the essential ingredients like the high IDT. So with the testbed, we verified that these waveforms cause meter errors similar to the original waveform they are based on, showing that these artificial waveforms are suitable for incorporation into new standards as test waveforms. So currently we are communicating our results and proposals with relevant standardization committees such as IEC and Senelec TC13, which are involved in meter testing, and regulatory bodies such as OIML and WELMEC, for those who are familiar with it. Okay. I would like to shift away from the effect of broadband signals on electricity meters to normalized methods now of measuring supraharmonic signals in the 2 to 150 kHz range in general. As you probably know, there's a growing evidence of product malfunction that is related to the conducted electromagnetic interference in this range. And there are 3 types of standards dealing with this problem. The first of them is defining emission limits, that is limits to the level of disturbances that electronic equipment is allowed to inject in the grid. And these are relevant for EV charging stations as well, of course. And other standards define immunity limits, that is limits to the level of interference that equipment should be able to withstand while properly functioning. So far, I was mainly talking about immunity of electricity meters. And EV charging stations also need to be tested against such standards, of course. There are also standards defining measurements methods, and because it turns out that interference levels can strongly depend on the measurement method. Obviously, this is important for everyone, actually. For power quality, the IEC 61000-4-30 is a well-known example that I will discuss more. I mentioned already there's several methods existing to measure the 2 to 150 kHz disturbances, and they are covered by different standardization bodies as well. This overview in this sheet is prepared a few years ago by Michael Schwenke from Siemens, who is also the convener of the IEC subcommittee 77A working group 9 that oversees the 61000-4-30. Currently, this standard refers to 3 different measurement methods in an informative annex only. It refers to the 61000-4-7 for frequencies up to 9 kHz, but it also has its own suggestion for frequencies beyond that limit, and it also refers to the CISPR 16 as an alternative. That is the standard that is developed for frequencies up to the megahertz regime, actually. Now, the idea is to have a new and better situation for the new edition 4 of the 4-30 standard in the near future. So why do they want to improve the present situation? Let me then first explain the differences. The 2 IEC methods are actually single-ended measurements, and they can be used in the laboratory, but also on site. The whole spectrum is measured, including the fundamental, the 50 Hz fundamental. However, there is a transition at 9 kHz because the computation time is an issue. as you can see in the 430 method, there's only 8% coverage in time as a result. And the CISPR standard actually provides two similar methods that are combined in this table. It is the peak and the quasi-peak detection methods, which are quite similar. The CISPR method uses an analog differential detector or a spectrum analyzer, which is meant for laboratory testing only. It uses an analog bandpass filter, which is sweeping over the whole frequency range, but it neglects the 50 Hz component. Unfortunately, Jan Meyer and his group in Dresden observed large differences when determining the emissions of different pieces of equipment, including EV charging stations. Note that the scale of the graphs here is logarithmic. It's in dB microvolt. These discrepancies have led to the SuperEMI project, which is on grid measurements of two 250 kHz harmonics to support normative emission limits for mass market electrical goods. And it provides metrological support to the IEC Subcommittee 77A Working Group 9, which I mentioned before, on the development of the new edition 4 of the 621,000-4-30 Annex C. So this SuperEMI project focuses on a metrologically sound proposal for a method to measure 250 kHz harmonics to be included in the 61,000-4-30 edition 4, using real-world signals to verify the applicability of the methods. And among others, NPL and TU Dresden were involved in a new proposed method that is a modification of the existing 4-7 method, such that no differences occur at 9 kHz. The 200 millisecond or 10 cycle time window is changed to 20 milliseconds, and the frequency steps of 100 Hz are made. And grouping is now done in 200 Hz windows. For reproducibility of the measurements, an artificial mains network is included. Sometimes that's also called a line impedance stabilization network. For specific measurements related to the CISPR 16 standard, a second option will be included as well, which is a digital implementation of the analog method, which is currently described in the CISPR standard. For verification purposes, VSL and LNE are now testing electronic appliances, including a PV inverter and also a converter for EV charging, where LNE performs the conventional CISPR measurements and VSL uses the proposed new method. And NPL and TUD will perform on-site measurements using the VSL waveform recorder that I described earlier. The new method is installed in this recorder to register supraharmonics, but also time domain waveforms will be recorded, such that this second option that I just mentioned can be tested in post-processing. Okay, this project is still running, so I don't have much more results at this stage, which brings me to the third topic that I will only shortly describe as well, because the project just started. But this is on power quality and low voltage DC grids. Apart from the familiar AC grids and the related power quality that you are familiar with, upcoming issue is power quality disturbances for DC systems and DC microgrids. EV charging stations are good examples of the the ambiguity of AC and DC, as you know, because you have both AC and DC chargers. As you know, also, despite the fact that the mains grid is AC, we are in fact living in a DC world. All our electronic and battery-driven devices use DC. And many of these devices are delivered with adapters to convert the AC from the wall socket to DC. And in that process, energy is wasted. We not only use DC, but we also, with the increasing use of renewable energy sources, we generate DC electricity. Currently, this electricity is first converted to AC, which you can see on the left, for connection to the grid, and then converted back to DC for use by DC electronic devices. Directly using this renewable energy, as you see on the right, as DC electricity is much more efficient. And also with DC power generation and storage at the same line, we have local DC microgrids, and households and businesses can then be semi-independent from the public AC distribution grid. Several grid trials are currently in place to test the benefits of such DC grids. For example, in Smart City Malaga, with micro wind turbines shown here on the picture. And also some EV charging stations are set up as DC microgrids. The implementation of DC grids brings, of course, challenges and some unknowns, and many of these are measurement related. So, for instance, power quality disturbances are currently very well managed and standardized in AC grids, but not yet in DC grids, because the disturbances are different. So this led to two express needs for metrology support in standards development for DC disturbances. The first one on the left is by Senelec TC8X, working group 1, who wants to include DC grids into the existing EN50160, which is on voltage characteristics. And they need metrology support to obtain proper power quality definitions for DC. They also need a practical measurement guide and a reliable method to determine realistic and well-defined power quality limits for DC grids. The second need is by IEC TC13 Working Group 11, who just developed a new standard for DC electricity meter testing, which is based on the existing standard for AC. It's more or less a one-to-one copy. But they need metrology support to investigate specific DC aspects for future revision of the standard. As an example, they mentioned the ripples in EV charging stations and the immunity of DC electricity meters against these ripples. So the Ampere project DC grids is a direct response to these expressed needs. And the needs can also be read from stakeholder support letters, which include grid operators, manufacturers of DC electricity meters, and also EV charging stations, even a car manufacturer, energy research companies and institutes, and a testing house, and of course, standard organizations. Yeah, the main problem is that DC grids are still in their infancy, and the behavior and origin of disturbances of DC grids is fundamentally different from AC. Also, equipment used for AC is usually not suitable for DC. Think of transformers, for instance, and usually specific DC equipment is not sufficiently broadband. So in this project, I mean, we realize on-site measurement equipment and reference calibration systems capable of accurately measuring DC signals with broadband distortions. And in specific, in the 4 technical work packages, we will develop new instrumentation and measurement algorithms to perform on-site measurement campaigns in the Netherlands and in Spain that I just showed in Malaga, but also at 2 EV charging stations in Germany. From these measurements, we will deduce new DC power quality definitions and analysis algorithms. We will also realize traceability for these parameters by developing new reference systems and test facilities. Also propose new severity indices and methodologies for power quality immunity level and planning level surveys for grid operators. Yeah, the project just started last month, so unfortunately there's not much more to tell you yet, unfortunately. Okay, this brings me to the end of my presentation. I've discussed 3 different topics with you. The first is the influence of broadband disturbances on electricity meters. I showed you that gross errors occurred for specific meters used using both laboratory waveforms and waveforms recorded at on-site metered supply points. These waveforms were applied to the meters using a new type of testbed, and a benchmark meter and waveform recorder was developed that is immune to these disturbances. And the results have been presented and discussed with several standards committees. The second topic was on the measurement methods of supraharmonics in support of IEC SE 77A Working Group 9 to improve the standard 61000-4-30. And 2 new methods have been proposed that are currently being tested using laboratory measurements on specific electronic appliances, among other an EV charging converter, and also on-site measurements. The third topic was power quality disturbances in DC grids, which are currently not defined yet. The idea is to develop DC broadband equipment and to perform on-site measurements to see what is actually present in DC grids, and then to derive new power quality definitions and measurement methods from these. And to guarantee traceability, reference systems and DC electricity meter test facilities will be developed. Okay, thank you for your attention. If you have questions, please ask them, or maybe you did already. I can't see the chat, so.
Yes, thank you, Helko, for your nice presentation. I think you gave a very nice overview, also some nice details and results on the work you have been done. And also your conclusion is important. There's still a lot of work to be done, especially in the measurement definitions of the 2 to 150 kHz and power quality for DC microgrids. So very important, very interesting. Thank you. We did receive some questions. I will start with one I had myself. So what do you think are at the moment the limitations before we can go to emission limits in the supraharmonic range? What knowledge is still missing? Can you comment on this?
Yeah, I think what is missing is what is real. So a lot of on-site measurements need to be performed. There have been done a lot of measurements already, but I think just as for the meter project, the first topic, we have seen new types of measurements that were not expected before, and I think that still some on-site measurements can be done, but with new algorithms, such that everyone agrees that these are the actual limits. So to set the limits, so you should really know how they are measured and how they should be measured. I think the latter is actually the most important limitation now.
Yes, so standardization on how are you measuring and how are you quantifying the amount of distortion you see in practice. That's important to think about.
I think so, yes.
Yeah. Okay, thank you. Another question from Artur Andruskiewicz. What is the best current sensor technology to avoid metering errors? And what about the supraharmonic impact on the meters itself, on the MID meters?
Yeah, there's 2 kinds of questions. The 2 type of answers. I mean, for testing, such as we did, we provide or we purchase current sensors that are sufficiently broadband and sufficiently reliable, and we test them. And actually, we used Rogowski coils in the on-site equipment, and we used shunts in our laboratory reference system. So in principle, both can be done. But what we have seen in the meters we have tested, in the meantime, we have tested, I think, 60 or 70 meters or so, at different types of meters, I mean. I should say among those, the ones with Rogowski coils showed the most errors. But that doesn't mean that shunts or CTs are completely good. Also, some Hall sensor meters have shown errors. But if I would do statistics, I would see that there are more errors on the Rogowski coils. And of course, meter manufacturers have the problem that they have to supply hundred thousands of meters, and they have to make them as cheap as possible. I think the total costs are on the order of well, 50 euros or something like that. So you cannot purchase or develop very expensive sensors, and every little component, if you do that times 100,000, is a lot of money. So that's the trade-off. But yeah, in the end, they have to find what is the best solution for them to change, either using other current sensors or maybe include I don't know, some simple filter element like just an inductor or something like that. But I would like to leave that up to them.
Well, thank you for your very elaborate answer on this question. Very interesting to think about indeed. Next question is from Matt Bollen. You mentioned that the biggest errors in energy metering occur for small loads, and he thinks that's actually good news, because what will be the potential impact on the monthly electricity bill of the consumer? Will it be some percent, or 9%, or 10%, or even more? What do you think?
Yeah, that's a good question. I think for the average user, actually, if they would have this specific water pump, for instance, that only draws, say, 10 or 20, I think 20 watt or so. So on the total energy bill, that would be negligible, only a few percent at most. But it's a rather principal matter, I think. So there will also be meter supply points where with a lot of LED or other kinds of installations that do cause these harmful waveforms. So yeah, so meters should be able to withstand them. But I think for the average user, on the total electricity bill, it's just order of percentage. But the point, of course, is when changing from one type of lamps to another type of lamps, you do that because you want to save energy. And if the result is that your energy bill will go up rather than go down, yeah, that doesn't feel good. Yeah.
No, indeed. Okay, there's time for one final question. This one is from Shamista. It's about LED lights. It can have quite large inverse currents while switching on and off. How can we make the smart meters to ignore this high peak? Is the LED manufacturer responsible, or should the smart meters be adapted to restrict the high peaks or the effect of them?
That's also a good question. Actually, we didn't take that into account. We only considered continuous signals. Yeah? So switching, in principle, yeah, I would say switching is just a very short moment. So the amount of energy related to that for the energy meter will hopefully, I don't know, but hopefully not be too large. But yeah, it's a good point. My gut feeling would be that filtering by just using an inductor would be sufficient to be protected against such sharp peaks. Yeah, we didn't investigate that. Okay.
Well, thank you again for your nice presentation and for your answer to the questions. there are still some open questions. We will send them to you by email, so you can still answer them to the askers.
Okay, thank you.
We're going to close the session. The next one will be after lunch. So at 1 o'clock, Zian Kin from the University Delft will be presenting about power quality and the power electronics perspective on this. So I hope to see you all there. And for now, hope to see you there. Bye-bye.
Okay, have a nice day.